Introduction. Our cosmic address. Space is vast. When we look up at the night sky, we are seeing just a tiny fraction of what's out there. Billions of galaxies, each containing billions of stars, stretch out in every direction. Where did it all come from? How did this immense and intricate universe come to be? These are questions that have captivated humans for centuries. Today, we have a scientific theory that offers a compelling explanation: the Big Bang. The Big Bang theory describes the origin and evolution of the universe. It tells the story of a universe that began from an extremely hot, dense state and has been expanding and cooling ever since. Imagine a time when the universe, as we know it, was confined to a space smaller than an atom. Then, about 13.8 billion years ago, something incredible happened. This point began to expand, and it's been expanding ever since. This wasn't an explosion in the traditional sense, like a firework going off in space. It was the expansion of space itself, carrying everything along with it. The expanding universe clues from the cosmos. The idea of an expanding universe was first proposed in the 1920s by Georges Lemaitre, a Belgian priest and physicist. Edwin Hubble, an American astronomer, provided observational evidence for Lemaitre's theory. In 1929, Hubble discovered that galaxies are moving away from us, and that their speed is proportional to their distance. This observation, now known as Hubble's law, revolutionized our understanding of the universe. Imagine baking a loaf of raisin bread. As the dough rises, the raisins embedded in it move farther apart. This is analogous to what's happening in the universe. The galaxies are like the raisins, and the expanding space-time fabric is like the rising dough. The expansion of the universe is a fundamental concept in modern cosmology. The Big Bang, a tiny seed of immense energy. The Big Bang theory describes the universe's beginning as a state of unimaginable density and temperature. All the matter and energy we see today were once concentrated in a volume smaller than a single atom. From this state of extreme density and temperature, the universe began to expand and cool. As the universe expanded, it cooled, and energy began to transform into matter. This process, governed by Einstein's famous equation E=mc2, gave rise to the particles that make up everything we see around us. In the first fraction of a second after the Big Bang, the universe was a chaotic soup of elementary particles. Quarks, leptons, and their antiparticles collided at unimaginable speeds. The Big Bang wasn't just an explosion of matter into pre-existing space. It was the expansion of space itself, creating time and space as it unfolded. The first few moments, a symphony of particles. The first few moments after the Big Bang were a flurry of activity. As the universe expanded and cooled, the energy of the early universe began to condense into particles. One of the key events in this early universe was the formation of protons and neutrons, the building blocks of atomic nuclei. These particles emerged from the primordial soup of quarks. As the universe continued to cool, protons and neutrons began to combine to form the first atomic nuclei. This process, known as Big Bang nucleosynthesis, occurred when the universe was a few minutes old. Big Bang nucleosynthesis produced mostly hydrogen and helium, along with trace amounts of lithium and beryllium. These elements would later become the building blocks of stars and galaxies. Imagine hearing a faint whisper from billions of years ago. That's essentially what astronomers have done by detecting the cosmic microwave background, or CMB radiation. This faint afterglow of the Big Bang is one of the most compelling pieces of evidence supporting the theory. Think of it as a baby picture of the universe, taken when it was just 380,000 years old. The CMB was discovered in 1964 by Arno Penzias and Robert Wilson, who initially thought the signal they were picking up was interference from pigeons roosting in their antenna. This radiation provides a snapshot of the universe when it was young and hot. The early universe was a rather simple place, dominated by hydrogen and helium, the lightest elements. But we know the universe is teeming with heavier elements like carbon, oxygen, and iron, essential for forming stars, planets, and even life itself. Stars are like giant cosmic furnaces fusing hydrogen and helium in their cores to create heavier elements. This process, known as stellar nucleosynthesis, is responsible for creating elements like carbon, nitrogen, and oxygen. As stars age and exhaust their nuclear fuel, they can explode as supernovae, scattering these newly formed elements into space. These stellar explosions enrich the interstellar medium, paving the way for the formation of new stars and planetary systems. We are, quite literally, stardust. As the universe continued to expand and cool, gravity began to exert its influence. Tiny density fluctuations in the early universe, amplified by gravity over millions of years, provided the seeds for the formation of stars and galaxies. These regions of slightly higher density attracted more and more matter, eventually collapsing under their own gravity. As these clouds of gas collapsed, they heated up, eventually reaching temperatures high enough to ignite nuclear fusion in their cores. This marked the birth of the first stars, colossal balls of hydrogen and helium that illuminated the early universe. These first stars were likely very different from the stars we see today, much more massive and short-lived. The first stars were not solitary wanderers but were grouped together in massive clusters. These clusters eventually coalesced to form the first galaxies. As we delve deeper into the mysteries of the universe, we encounter phenomena that challenge our current understanding of physics. One of the most profound discoveries in recent decades is that most of the universe is not made up of the matter we are familiar with. In fact, a staggering 85% of the matter in the universe is made up of something called dark matter. Dark matter doesn't interact with light, making it invisible to our telescopes. We can, however, infer its presence through its gravitational effects on visible matter. The rotation of galaxies, for example, is far too fast to be explained by the visible matter alone. This discrepancy suggests the presence of a hidden mass, hence the term dark matter. In the late 1990s, astronomers made another startling discovery. The expansion of the universe is accelerating. This discovery implies the existence of a mysterious force that counteracts gravity, pushing everything apart at an ever-increasing rate. This force has been dubbed dark energy. The Big Bang Theory describes the origin and evolution of our observable universe. But what if our universe is just one of many? The idea of a multiverse, a collection of universes coexisting like bubbles in a cosmic foam, has captured the imagination of physicists and science fiction writers alike. The multiverse hypothesis arises from several theoretical frameworks, including string theory and inflationary cosmology. String theory suggests the existence of extraspatial dimensions beyond the three we experience. These extra dimensions could potentially host other universes, each with its own set of physical laws and constants. While the multiverse hypothesis is intriguing, it's important to note that it remains highly speculative. We currently lack any direct observational evidence for the existence of other universes. Despite the remarkable progress we've made in understanding the universe, many mysteries remain. The Big Bang Theory, while incredibly successful in explaining a wide range of observations, is not a complete theory. One of the biggest mysteries is the nature of dark matter and dark energy. These invisible components make up the vast majority of the universe, yet we know very little about them. What are they made of? How do they interact with each other and with ordinary matter? Answering these questions is crucial for understanding the evolution and fate of the universe. Another open question is what caused the Big Bang itself. What existed before the Big Bang, if anything? To probe the very beginning of the universe, we need new physics, a theory of quantum gravity that can unify general relativity with quantum mechanics. The Big Bang Theory, a testament to human curiosity and ingenuity, has revolutionized our understanding of the universe. It tells the story of a universe that began from an incredibly hot, dense state and has been expanding and cooling ever since. From this primordial soup emerged stars, galaxies, planets, and eventually, life itself. As we look up at the night sky, we are gazing into the past. The light from distant stars and galaxies has traveled for millions, even billions of years to reach us. The journey of the universe from the Big Bang to the present day is a story of transformation, complexity, and interconnectedness. We are, in a very real sense, children of the Big Bang, and our journey of cosmic exploration is just beginning.